and turn the floor over to Nicolas Gisin, who will be speaking on indeterminism in physics and intuitionistic mathematics. So let me...
Okay, so I'll start about 15 minutes early. That's correct?
Yes, sorry about that. I think we're going to have, I will have some, soon we're going to have a break so we can actually catch up to the advertised schedule. I think that that was a fault of yesterday's proceedings, and I apologize. I actually thought it would take longer than I did, but it didn't. So, so Nicolas, you are now can share your.
Okay, so I'll share my screen. So do you see what should be on my title?
Yes.
Okay, very good. So let's start. Well, so thank you for the introduction. Thank you for the invitation. As you said, I'm going to talk about indeterminism in physics and intuitionistic mathematics. And it may sound a bit strange that a physicist, so I'm a physicist, it says here that I'm a member of this group of applied physics in Geneva. So what does a physicist have to say about foundations of mathematics, which seem to be quite foreign from physics? Yeah, so why does a physicist talk about intuitionistic mathematics? Well, I think we all know that actually physics and mathematics have a very close connection through history, and including today's history, discoveries and developments. And indeed, to do physics, well, we speak mathematics. Yeah, here. We speak mathematics, so we need physical concepts, but also appropriate mathematical tools and concepts. So when we speak mathematics, I have to say during most of my career, I didn't really thought much about that. I just used the mathematics that I was that I learned at school and university. But of course, the question is, which mathematics, which mathematical language? And certainly we all know here, I guess, we all speak more than one language. We know accordingly that depending on the language we speak, some ideas are easier to express than others. And so changing the mathematical language may indeed change the way we can express physical ideas. Maybe it gives new ideas or just allows us to express the ideas a bit differently. Now, this intuitionistic mathematics, which I personally discovered barely about a year ago, over a year ago, so I'm not a specialist of intuitionistic mathematics, I wouldn't claim so. And actually, the Brouwer, a Dutch mathematician who is the father of intuitionism, he introduced into his intuitionistic mathematics the concept of an ideal mathematician, or a creating subject, who continuously produces new information by solving mathematical conjectures. And that's a very idealistic point of view, and Brouwer was indeed a very idealistic, almost a solipsist. And certainly that's not adequate for physics a priori. Physicists are more realists. And it is certainly not my way of presenting intuitionism. So I'm going to present intuitionism without this ideal mathematician and motivated by the physical concept of indeterminism. Accordingly, it is very possible that Brouwer himself would not have liked my presentation, and possibly also some of today's intuitionists. Again, I'm a physicist, maybe a naive realist. So the main claim of my talk today is that intuitionistic mathematics is a natural mathematical tool to describe indeterminism in physics, like derivative is a natural tool to describe velocity. So let's start. Numbers was already mentioned in the introduction. What are numbers? Especially for physicists, we would think in computer science, numbers are there to compute. However, how can it be then that most of the so-called real numbers are actually not computable? There's no finite algorithm that allows you to compute these real numbers. That's the first hint, maybe, just to start, I don't know, spreading the virus of intuitionism. Hopefully, it is also a bit contagious, but it doesn't harm. So let me define some integers taken from Bishop. The first integer, very simple, n1 equals 0 if every even integer between 4 and, let's say, 10,000 is the sum of 2 primes, and n1 equal 1 otherwise. So possibly some of you don't know the answer, so you don't know the value of n1. But obviously, if you take a computer and spend a minute on it, you will find out that n1 is equal to 0. It's very simple to compute and to test. n2 equals 0 if every even integer between 4 and a huge number, but a finite number, is the sum of 2 primes, and n2 equal 1 otherwise. So here, it's not useful to go to a computer because it's going to take an awful long time, or maybe just too long, and so we may never know the value of n2. But it's also clear that to compute n2 is a matter of a finite time, a long but a finite time. So although we don't know n2, I guess we would all agree that n2 has a determined value, either n2 equals 0 or n2 equal 1. Let's come to the most interesting, n3. n3 equals 0 if every even integer larger than 4 without any upper bound is the sum of 2 primes, and n3 equal 1 otherwise. So that's a Goldbach conjecture. So n3, not only do we not know its value, but there is no finite algorithm that is going to give us, no known finite algorithm that is going to tell us what is the value of n3. So here is where intuitionism starts to differ significantly, deeply from standard classical mathematics. n3, according to intuitionism, has no value, or more precisely, it doesn't have the value 0, it doesn't have the value 1. It is indeterminate. And so if we now ask a standard mathematics student what is the value of n3, probably the student would say that in order not to fail the exam, he has to claim that n3 has a determined value, because that's what he learns at school. Except if that is an exam in intuitionistic mathematics, then the student should answer that the value of n3 is indeterminate, and that the law of the excluded middle is thus not valid, because it is not either equal to 0 or not equal to 0. It could be, there is this third possibility of being indeterminate. Moreover, there is one thing more. Of course, it could be that in the future, at some point in time, some clever mathematician solves this Goldbach conjecture and finds out, well, that n3 is equal to 0, or finds out that n3 is equal to 1. So it could be also that the value of n3 may evolve over time from indeterminate to determinate. So that's certainly shocking, surprising to classical mathematicians and to most of my physics colleagues, certainly, because you have a number that has as a value indeterminate, and moreover, the value of this number n3 may change and evolve over time. Let's look a bit more into that, and here I like just to quote a bit some colleagues. Karl Possi, a philosopher in Jerusalem, who wrote, "We humans have finite memories, finite attention spans, and finite lives. So we can fully grasp only finitely many finite-sized pieces of a compound thing. There is no infinite helicopter allowing us to survey the whole terrain or to tell how things will look at the end of time." So you can see what is just here, the finiteness, but you cannot see the entire future. You cannot have a look from the end of time. Or Bishop wrote, the classicist wishes to describe God's mathematics. The constructivist, and intuitionism is part of constructive mathematics, to describe the mathematics of finite beings, man's mathematics for short. Constructive mathematics does not postulate a pre-existing universe with objects lying around waiting to be collected and grouped into sets like shells on a beach. And Brouwer himself, nature simply has not yet fully determined all objects. Now, if that would be physics, especially quantum physics, we would just mention Heisenberg uncertainty principle or indeterminacy principle to be more precise. But here, Brouwer extends that even to mathematical objects. And that's really the essence of intuitionism. And possibly some of you or of my colleagues start to get worried, but with this kind of intuitionistic mathematics, could it really be that there are objects that are not fully determined? And here maybe I want immediately to calm these kind of worries with the pretty obvious statement that with intuitionistic or finite mathematics, you can compute and prove theorems. You can make all the same computation, obviously, but the theorems are not always the same as in classical mathematics, and I will see several examples. And also, sometimes the theorems are the same, but the way to prove them may be very different. And obviously, everything you can do on a classical computer, it can be done in intuitionistic mathematics. Maybe even more, if I take an example, a very timely example of a very active branch of physics, namely climate physics, the colleagues studying climate physics, how do they do? They want to know the climate or to predict the climate under certain assumptions in 50 years or even more. And they use truncated numbers, so finite numbers, no real numbers, of course, because it's in a computer. And then at some point in time, they need to add additional digits. How do they do that? Well, they use stochastic reminders. So actually, climate physics is today done with intuitionistic mathematics, except that my colleagues in climate physics probably are not aware that we are doing that. Another way also of, and that was now my motivation that came before intuitionism, comes a bit from this kind of picture, you know, that there is this big tension between relativity on one side and quantum mechanics on the other side. So on one side, you have this block universe where everything is fixed and frozen since ever and forever. And on the other side, with this little picture of a quantum random number generator, we have a theory which describes the creation, the continual creation of new information as time passes. So let me tell you a bit about my motivation, how I came to that, and I was about to reinvent intuitionism when I actually discovered that this was already existing. So I was studying more classical chaotic dynamical systems, and you know, this is classical mechanics, is something super well known. We also understand the boundaries of this theory, and that's all very good. And it's also a pretty typical example of a physics theory. And usually one talks about deterministic chaos. But is that really so? Or is it the consequence of the language of classical mathematics, assuming a God's eye view or a view from the end of time? Another philosopher in Jerusalem, Yuval Dolev, wrote, "Tense and passage are not, never were, and probably cannot be part of physics and its language." And I think Dolev is certainly correct if we use classical mathematics, because there we look at everything from the end of time, so there is no passage of time, it's already all there. But if we change the language, it could be that Yuval Dolev is wrong. So let's look at a simple example of a chaotic system. Essentially, the Baker's map is well known. So the state space is just the continuum between 0 and 1. You stretch it by multiplying by 2, then you fold it back. And so mathematically, you have this little equation. And if you write now x in binary format, so you start with a 0 dot, and then you have the list of bits. And then this function is just a shift function. So the second bit becomes the first, the third becomes the second, and so on. So here also we see obviously that this is chaotic because very quickly the far down the series bits will become relevant and dominating. And so whether x lies on the left or right half after n steps depends obviously on the nth bit of the initial condition. Now this could be, for instance, the probability of rain, so sunny for low values, rainy for large values. And so whether it will be rainy in a million time steps depends on the million initial bits of the initial condition. And then we can ask ourselves, that's the questions I was asking myself, is the millionth bit physically real? According to classical mathematics, obviously it is real, but is it physically real? And certainly the question here that I'm interested in is not whether this millionth bit can be measured. Obviously we cannot measure it, but that's not the point. But the question is, does it correspond to something physical? And now let's look at this typical real number. What is really strange is that all real numbers one encounters in one's career, except maybe for some mathematicians that are very specialized in that, all these real numbers one encounters are actually exceptional. They're exceptional only by the fact that they have a name, and they only countably many names. Or they are defined by an algorithm. Again, there are only countably many algorithms. So here are examples of numbers that you have certainly already encountered. But the bits of typical real numbers have no structure. The bits are random, and they are as random as quantum measurement outcomes. So for physicists, the bits of a typical real number is as random as possible. And maybe a good way, at least for a physicist or a quantum physicist like myself, to think of a typical real number is just the string of bits that come out of a quantum random number generator. A source of photons, a beam splitter, two detectors. One detector you name 0, the other one you count as a 1. And then you get a string of bits, and that defines a typical real number. And actually, we can go further than that. I already said there are only countably many names and algorithms. And also something that Emil Brouwer mentioned, which I also find quite interesting, although it's pretty obvious. Since in a real number, you have this infinite string of bits, so you have infinite information. And with infinite information, you can, of course, put an infinite amount of information in it. So in particular, you could code the answers to all questions one could formulate in any human language. And so what actually Gregory Gisin emphasizes in this paper here is that not only can one think of the outcome of a random number generator as a typical real number, but that this is probably the only good way of thinking of typical real numbers. It's really the unlimited string of outputs of a true random number generator. So when we, the physicists, say, for instance, let's x0 be a real number, what we effectively say, let x0 denote an infinite amount of information about the initial condition, for instance. Now here, an argument, and this argument, you buy it or not, but I think it connects also to the theme of the workshop, and it's also, my way of presenting things. So let's suppose you have a finite volume of space, cubic centimeter, and the assumption here is that a finite volume of space cannot contain more than a finite number of bits, or cannot contain infinitely many bits. And then if you have a billiard ball or a marble in your finite space, then the position of the center of mass of this classical particle cannot be a real number, because typically real numbers have infinite information. Of course, here I could now call the Bekenstein theorem or bounds and call for, I don't know, relativity, black holes, quantum field theory. But I think this assumption that a finite volume of space cannot contain infinitely many bits is something that we can accept intuitively without calling general relativity and black holes. Yeah, and that's something I have mentioned in this paper that you see here on the bottom, which, by the way, appeared in a philosophy journal, not in a physics and not in a mathematics journal. And okay, obviously, it is not because Descartes named real the so-called real numbers that they are really real. So somehow the conclusion here, and we're going to develop that with intuitionistic mathematics, is that mathematical real numbers of classical mathematics, they are not physically real. On the contrary, mathematical real numbers are physically random. And of course, now random numbers, if instead of Descartes, we would have someone else who would have named these real numbers random numbers, which would be a more appropriate terminology, then these random numbers would never have become the basis of scientific determinism. So it changes really also, and that's, we see here that changing the language changes also the way one perceives things. So at this point, one may think of a real number between 0 and 1 or something like that. You have the first digits that are clearly determined, and then you get a region where the bits or the digits here gets blurred, and after some point, they are just fully indeterminate. Okay, and at that point, once you get to consider now that classical mechanics, especially in the chaotic case, is indeterministic, then like for quantum mechanics, you may say, okay, let's just add some additional variables. Let's do like Einstein said, we need some additional variables to turn the theory deterministic. Essentially, the idea is that instead of God playing dice, when potentialities become actual, let's assume that God played all dice at the initial time and coded all results of these dice into the initial condition. So we face a choice. Either the fact that at present certain things happen and others do not is interpreted as revealing retroactively information about long past initial conditions, or else we understand the present was the result of indeterminate reality and the future is open. Now, clearly, if we are thinking now of this classical chaotic dynamical system, what are the hidden variables that we should add? Well, it is just the real numbers. So the real numbers, one could think here, are the hidden variables of classical mechanics. And it is a fact that almost all physicists accept real numbers without even noticing that they are somehow supplementary variables. But the same physicists would reject Brownian positions as unnecessary. So I'm not going to elaborate, but in quantum mechanics, we also have indeterminism, and there are several ways around that if one wants. And one sort of non-local hidden variables are Brownian positions. And these ones are rejected by almost all physicists who at the same time accept real numbers without hesitation. Both from this point of view that I'm presenting here, consistency should be able to accept the real numbers and the Brownian positions or to reject both of them. Okay, just a picture of these huge debates that we all know, Einstein-Bohr, Einstein and Bergson, the master of philosophy in the early 20th century. And there was another big debate, a bit less known, at least it was not known to me 1.5 years ago, between Hilbert and Brouwer. So David Hilbert, that's the huge mathematicians that we all know about. And for him, so let's say the father of classical mathematics, for whom every real number is an individual completed entity. All digits are given at once, and the continuum is just a collection of individual points. So real numbers here exist outside of time in some ideal Platonistic world. That's the standard mathematics that one learns. And on the other side, you have Brouwer with his intuitionistic mathematics, where real numbers are processes that develop in time. I'll come back to that. So digits are not all given at once, okay, except computable numbers, I would say. And the continuum is a viscous collection, I'll come back to explain that, of processes. And so here in intuitionistic mathematics, time is essential, since at any instant, at any finite time, only finite information exists. So let's go into intuitionistic mathematics a bit deeper. Brouwer introduced the concept of choice sequences, alpha of n. So at every instant n, we have a number alpha n. Okay, according to Brouwer, these choices to choose the next element of the sequence was made by this idealized mathematician. But let's change that a bit, I think keeping the spirit the following way. So just make the assumption that nature has the power to produce true randomness. So to produce new information. And if you want to describe indeterminism, by definition, I would say, means that indeed nature has the power to produce new information. So at each time step or each instant n, so n will be an integer, a natural random process outputs some random numbers. So this natural random process produces, and okay, here I will talk about bits, but it could be any finite information here, which is the new information. Now this new information is used to define the next element of the choice sequence, which is a function, a computable function of the previous value in the choice sequence of the instant or time step n, and of the available existing information. So it cannot depend on the future, but it depends on the past up to the present. So this function is computable. So of course, all these functions alpha n are also, all these numbers alpha n are also computable. And here I make a bit of a difference with what standard intuitionism says in two ways. First, here I don't assume rationals, I assume computable numbers. And I will explain why. I think for physics, it's much more convenient to have computable numbers rather than rationals here. And secondly, there's an example that I want to give here where convergence of this choice sequence or this series of alpha n happens only with probability 1, while usually intuitionists require convergence with certainty. Again, I think that we should be a bit more relaxed here if we want to apply that to physics. So let's have examples. The first example is a pretty trivial one. So you take the previous computable number and you just add as the next digit what comes out of the random number generator. So as this natural random process. So this is exactly what I presented before with my quantum random number generator that was producing or outputting the bits of a typical real number. And so these ones, maybe we could call them the totally random numbers. Of course, there are also computable numbers. We already heard of pi. More generally, we could also think of any pseudo-random series that all our classical computers are able to produce for cryptography or Monte Carlo calculation and so on. So in this language, it would just mean that this function does not depend on all the past, all the information that exists, but only on k bits. And these k bits are the seed of pseudo-random number generators. So this is an example clearly of something that fits here in, but is not a typical intuitionistic number. Maybe one thing about pi, and here I guess I'm not going to agree with John, who made the introduction, but let me nevertheless tell my view here. So pi is a typical computable number, and all bits can be computed because they are all determined by a finite algorithm. And may take time to run the algorithm, but every bit can be computed in a finite time. So far, we all agree. Now, what is really, I think, very interesting, again, in my context, although the bits may look random, and they are hidden by the algorithm, kind of pseudo-random in some sense, the following algorithm, which I wrote here, which you can find more on this Wikipedia page, allows one to compute directly the nth hexadecimal of pi without computing all the previous bits. And that's very different from classical chaotic dynamical systems. Think about the weather, which is a typical chaotic system. The weather in 2 years' time is today indeterminate. That's okay. That's the view that I'm proposing, that the future is open. So the time in 2 years, the weather in 2 years' time, let's say at Piccadilly Circus in London, is undetermined. Now, in order to know the weather, we just have to wait. We wait 2 years, and of course, in 2 years' time, we'll know. But if we wait 2 years, we necessarily first wait 1 year. So we'll also know the weather in 1 year. Here with the digits of pi, or the hexadecimals more precisely, or the bits of pi, one can jump ahead. One doesn't need to compute all the intermediate or previous bits. One can directly jump to bits 1 million, for instance. So that's a deep difference between computable number and, let's say, numbers that are undetermined. Okay, that's what I just said. Here another example of intuitionistic number, which I think is especially well suited for physics. I call them finite information quantity, and actually we introduced that with a colleague here in this paper before knowing intuitionistic mathematics. So here the idea is again that you start from the previous element of the choice sequence and you add one bit, but this bit that you add is just a majority vote over the k last random bits, with k being odd, let's say, to guarantee that there is a majority. And so in this case, you will have something, let's say again, it starts with a 0 in this example, and then you will have a few bits that are fully determined. If you go far into the future or down the series, of course, these bits are totally undetermined because they are further away. But in between, you have bits which are maybe not yet fully determined, but there might be already some kind of majority. And so if the majority is already very large, you know that you're not going to overthrow this majority immediately. So you may have some transition here over k bits, which represent some propensities, some intrinsic propensities of these bits. I think that's pretty close, at least to my intuition about numbers that we would use in physics. And here are some examples. Let's say you have already these bits, 1, 1, 0, 1, 1. Then, of course, the fifth bit is a 1 because a majority is a 1. But then if you're looking at the next one, well, here you have already 3 1s. So there's no way to get a majority different from 1. So you again have a 1. The next one, okay, there's still a large chance of having a 1, but it's only a 3/4 chance. So I don't write here a bit, but I write a fraction, and so on for the next one. Okay, let's go to other very typical intuitionistic numbers. Here I define the number, just alpha n is 1/2 plus -1 to the power of the nth random bit, 10 minus n. So clearly, if n is equal to 0, then we have a number which is slightly larger than 1/2, in the other case slightly smaller. So this number alpha n fluctuates around 1/2. But now we have the following rule. That goes on, this process goes on until, by chance, the last half random bits happen to all have the same value, all 0 or all 1. And n is even larger than 4. So here you see that as long as this mortal number, this process is ongoing, it's fluctuating. You cannot say it's smaller or larger than 1/2, it just fluctuates. Possibly, eventually, it tends to 1/2, but possibly, by chance, at some point, it stops. And it could stop just above 1/2 or just below 1/2. Okay. And indeed, here the rule is chosen such that the probability of termination, of dying of this number, decreases exponentially, so that there is an a priori probability that the sequence goes on forever. So you cannot be sure that the process will terminate or stop at some point. It might go on forever. And so in this case, very clearly, a proposition like alpha smaller than 1/2 is never true, as long as the process is ongoing, because it's just fluctuating. It's not false, it is indeterminate. So again, we have here an example of a number whose value may change in course of time, and again, an example where the law of the excluded middle does not hold. And here is my last example of numbers, which I call an autonomous number. So, previously in all examples, the function was explicitly depending on n. And here, I don't want that. And to avoid that, but still have convergence with probability 1, I put this function here. And you see that 1 and 0 are fixed points here, because once alpha n is equal to 1, then it doesn't change, because here this is 0, alpha equals 0, this doesn't change. So you have two fixed points, and actually more than that, alpha n converges to 1 or to 0 with these probabilities. Now, why am I interested in that one? Here I see a very close connection with something that I know from quantum mechanics. So one way of answering the question of the measurement problem in quantum mechanics is to consider stochastic Schrödinger equation, like Girardi-Rimini-Weber here, something that I contributed to here, there's quantum state diffusion. And with these stochastic Schrödinger equations, as time passes, you look here at the mean photon number, and let's suppose that the initial state is a superposition of photon number 1, 3, 5, 7, and 9, just as an example. And it's easy to prove that with these stochastic equations, each solution converges to an eigenstate. And it converges to the eigenstate with the standard quantum probability. So you recover also Born's rule. But you go to an eigenstate, and it's illustrated here. And if you would look more into the stochastic equations, which I'm not going to do here, these equations are really very much of that sort. It's very much the same sort of equation, and now you have it also on the classical side and not only on the quantum side. So here somehow what I'm doing is to bring classical mechanics closer to quantum. There are many people since a century or more than a century who tried to bring quantum closer to classical, but maybe we should do exactly the opposite. Okay, let's continue our discovery of intuitionism, and here with intuitionistic logic. So time is essential, and a statement, of course, that a random number, what comes out of this natural random process at time instance n is indeterminate before that time step. But also, as I already said, some of these statements like alpha smaller than 1/2 may be indeterminate, because some of processes may end up on 1/2, but you don't know as long as they did not die. And that's similar to this proposition about the weather at Piccadilly Circus. And so the law of the excluded middle is not valid in intuitionistic mathematics. And that's probably a shock to standard mathematicians, or most of them, because it makes non-constructive existence proof impossible. It does not, because you prove something, the negation of something does not guarantee that the proposition is true. That's surprising. But again, if you think in terms of an indeterministic world, or if you think in terms of a finite world where everything, including information, is finite, and of course time is open, so into the future is open, then I think this non-existence of this law of the excluded middle makes a lot of sense. And again, Brouwer said this law of excluded middle fails because the world is not determinate, so truth about it are indeterminate. So the continuum, let's say the continuum between 0 and 1, or the entire real line, they are evolving sequences of computable numbers. So Brouwer would have said here of rationals, but computable numbers for today. And some sequences just never terminate. They continue to fluctuate around 1/2. And so that has a huge consequence. It just means that you cannot cut the continuum into larger and smaller 1/2. You know, this continuum, you cannot just pick out one point out of it because it's not made out of points, contrary to the classical continuum. So you cannot just say, okay, oh, this 1/2 I take out of it. Or I define a function that takes a step function, for instance, that would have value 0 below 1/2 and 1 larger or equal to 1/2. And so this is one of the Brouwer's theorem, a famous theorem that says that all total functions, so function defined on every point, are continuous, no step function. So this is a theorem which is clearly valid in intuitionistic mathematics, but which is also obviously not valid in classical mathematics. Step functions exist in classical mathematics because there you can pick out this 1/2 out of the line. And in this sense, the intuitionistic continuum is viscous. It's like honey. You cannot take just, you know, an atom of honey or a molecule of honey out of honey. It sticks. It's viscous. Now, a classical theorem, which is also not valid intuitionistically, is the intermediate value theorem. Or if you have a function, a continuous function that starts negative, that later, a larger value, is positive, it has to cross 0. Here you cannot prove it in intuitionistic mathematics because you cannot construct the point at which it crosses 0. This may sound really very bad news to apply intuitionistic mathematics, but actually it's an example where there is another theorem which is valid intuitionistically and which is in practice just as good as the intermediate value theorem. So this intuitionistic theorem says the following: if you have a continuous function, starts negative, becomes positive, then for every positive epsilon you can construct in a finite time a value of x between a and b such that the absolute value of f of x is smaller than epsilon. So this is actually, at least for physicists, we never need more than that. We never need the intermediate value theorem. We need that version of the intermediate value theorem, which is a version which is valid intuitionistically. Another example of a theorem well known to quantum physicists is Gisin's theorem. And indeed, the standard proof of Gisin's theorem does not hold intuitionistically. So for some time, there was a bit of controversy here until Richman proved that actually Gisin's theorem can be proven, but it's a different sort of proof in a constructive way. So here we have examples of theorems that are completely new that do not exist classically, or here a way of replacing a classical theorem by another one, which is good enough in practice. And here, Gisin's theorem, where the theorem is maintains, but you have to change the way to prove it. Arithmetics, of course, we want to be able to define additions and sinuses or exponentials. And this is where why I defined my choice sequences to take values among the computable numbers, because I want these kind of computable functions for integrable classical dynamical systems to still lead valid choice sequences. Alpha larger than beta by definition, and you just copy the classical definition, but you insist that these integers k and n can be constructed. It's not enough to say that they exist, but you have to be able to construct them. And because of that, this relation is only a partial order. So for instance, alpha equals alpha equal beta, or alpha smaller or alpha larger than beta does not necessarily hold. But you have another new kind of an interesting concept. Alpha and beta are said to be apart if one constructs k and n, so integers, such that this absolute value of this difference is larger than 2 to the power minus k. So somehow intuitively it means that you can put your finger, okay, a finitely sized finger, in between alpha and beta. And now you have that indeed, if two intuitionistic numbers are not apart, then they are equal. But you have no law of the excluded middle, so you cannot reverse that implication, and you cannot say that not equal implies being apart. You have to think a bit more, but that's really the intuitionistic thinking, and it is very, I guess a physicist thinking about that would say, oh yes, that's obvious, because I think that's the way we think. Axiom of choice. So here I'm going a bit outside strictly intuitionistic mathematics, because for intuitionistic mathematics, the axiom of choice makes no sense. But let me just say a few words, because I think it is kind of connected, again, if you have also this idea of indeterminism. So this axiom says that whatever collection of non-empty sets AX, there exists a function that picks one element out of each of these non-empty sets. So in some sense, you say, okay, that's obvious, because the sets are non-empty, of course I can take an element out of them. But remember now, this index x here could be infinite and even continuously infinite. So you may also say that this looks absurd, this axiom, because it assumes the possibility to make a continuous infinity of choices in a finite time, or in actually no time. And of course, that's the reason why intuitionists would not even mention that. So this axiom of choice gives us a superb feeling of power. No? In a single stroke, one can do a continuous infinity of choices. So we are godlike. Again, that's the God's mathematics. So maybe a nice feeling for some of us. But when you apply that to the real world, to physics, I think it is absurd. And there is indeed one prediction, one consequence of the axiom of choice, which should shock every physicist, or at least every physicist or philosopher who considers that the future is open. Namely, the axiom of choice implies the existence, but of course it's a non-constructive existence proof, of a function that predicts with probability 1 all future events, including the outcomes of true random number generator. So the axiom of choice tells you, actually the future is there. There's no choice. There's nothing like a random number or a random number generator, or quantum mechanics is an illusion, and so on. So I guess the natural way to answer that is, okay, axiom of choice maybe for Platonistic mathematics is nice, and I have no problem if some mathematicians use it, but for mathematical physics, or just for physics, forget it. Okay, I'm coming. Here. I already said mathematical language uses that we use has a huge influence. So this is my almost last slide, where I compare concepts that are natural in indeterministic physics, and here concepts of intuitionistic mathematics. So according to indeterministic physics, the past, present, and future are not all given at once. And the future is not yet there. And indeed, according to intuitionistic mathematics, the digits, bits of real numbers, are not all given at once. They are not yet there. Time passes. Numbers are processes. Indeterminism, numbers contain finite information. So I think this idea of finite information implies indeterminism, is intimately connected to indeterminism. The present is thick. According to this block universe, the present is an infinitely thin slice of dimension 0. of the block universe. I think many physicists will share the intuition that the present cannot be something of measure zero. The present is where we live. That has some thickness. And maybe this is connected to the intuitionistic view that the continuum is viscous. You cannot just pick out a point. The future is open. No law of the excluded middle. The future is open. A proposition about the future has no value, or no true value, has the value indeterminate. Becoming choice sequences, experiencing intuitionism. Okay, so of course one could write probably a paper for each of the line of this slide, but let me conclude here. Maybe the only last thing I want to say on this last slide, which is a kind of summary, is to recall what Bishop said. Classical mathematics can be regarded as a branch of constructive mathematics. Take constructive mathematics, add some axioms, you will get classical mathematics. Whereas to regard constructive mathematics as a branch of classical mathematics is not possible, because you would have to take away some axioms. Okay, so thank you very much. I hope you could all listen and see everything I tried to convey. And looking forward to the remaining of this exciting day and evening for me.
Okay, thank you very much, Nicolas. Very fascinating talk. We'll have a chance